The story of quantum physics begins in the late 19th century, a period bustling with industrial growth and scientific discovery. It was during this era that scientists first encountered phenomena that could not be explained by classical physics. This puzzlement centered around the behavior of light and the atomic structure, which seemed to contradict everything known at that time. Classical physics, which included the laws of Newton and Maxwell, was unable to provide answers to certain experimental results, such as the black-body radiation problem and the photoelectric effect. These discrepancies led to a profound rethinking of the foundational principles of physics. The first quantum concept was introduced by Max Planck in 1900. He proposed that energy is quantized, meaning it could only be exchanged in discrete amounts, which he termed quanta. This radical idea was initially met with skepticism, but it fundamentally altered our understanding of energy and matter. Following Planck, Albert Einstein further challenged classical norms by suggesting that light could be described as discrete packets of energy, which he called photons. The introduction of quantization helped resolve the black-body radiation problem, demonstrating that classical physics was not equipped to explain all natural phenomena. Meanwhile, the photoelectric effect, explained by Einstein, showed that light could exhibit properties of both waves and particles. This duality was one of the first indicators of the quantum world's complexity, setting the stage for deeper and more perplexing discoveries. Each revelation peeled back layers of the atomic world, revealing a realm far stranger and more wonderful than anyone had anticipated. This early period of discovery was marked by intense debate and intellectual upheaval. The concepts introduced were so revolutionary that they required a new framework for understanding the physical world. This was the beginning of quantum physics, a field that continues to challenge our perceptions and expand our horizons. It is a testament to the relentless curiosity of scientists who dared to look beyond the visible, pushing the boundaries of what was considered possible. Wave-particle duality is one of the most intriguing and fundamental aspects of quantum physics. It posits that every particle or quantum entity can exhibit both particle-like and wave-like behavior, depending on the experiment conducted. This concept was first brought into the limelight by the double-slit experiment, conducted by Thomas Young in the early 19th century, which demonstrated light's wave-like properties. Later, scientists realized that electrons, which were thought to be merely particles, also exhibited wave-like characteristics under certain conditions. The implications of wave-particle duality are profound and counterintuitive. For instance, if you fire electrons at a barrier with two slits and then detect them on a screen on the other side, they create an interference pattern typical of waves, not particles. This pattern occurs even if electrons are fired one at a time, suggesting each electron interferes with itself as both a particle and a wave. This dual nature challenges the classical idea of an object being in one state at a time, fundamentally shaking the foundations of how we perceive reality. Moreover, the principle of wave-particle duality leads directly to the Heisenberg uncertainty principle. This principle states that certain pairs of properties, like position and momentum, cannot both be precisely measured at the same time. The more accurately we know one, the less accurately we can know the other. This is not due to experimental imperfections, but is a fundamental property of the quantum world, stemming from the dual nature of quantum objects. Understanding wave-particle duality thus opens the door to a universe where our classical intuition is no longer a reliable guide. It invites us to think about reality in new and often non-intuitive ways, paving the way for further explorations into the quantum domain. This concept not only perplexes, but also enriches our understanding of the universe, demonstrating the nuanced and interconnected nature of all things at the quantum level. The principle of superposition states that a quantum system can be in multiple states at the same time until it is observed. This idea was famously illustrated by Erwin Schrödinger's thought experiment involving a cat that is simultaneously alive and dead until someone looks inside the box. Although a macroscopic superposition like Schrödinger's cat remains theoretical, Superposition is routinely observed at the atomic and subatomic levels. This principle fundamentally questions the deterministic nature of the universe proposed by classical physics, suggesting a probabilistic approach to understanding physical systems. Superposition leads directly into the realm of quantum uncertainty, a concept that Werner Heisenberg formulated in 1927. Heisenberg's uncertainty principle is not just about the limits of measurement, but about the intrinsic nature of quantum states. For example, the more precisely you try to measure the position of a particle, the less precisely you can know its momentum, and vice versa. This uncertainty is not a technical deficiency or a lack of precision in our instruments. Rather, it is a fundamental aspect of how quantities are defined in the quantum realm. These concepts challenge our everyday experiences where objects have definite properties and outcomes are predictable. In the quantum world, objects exist in a spread of possible states, and only when we perform a measurement do these possibilities collapse into one state. This phenomenon has profound implications for the nature of reality, suggesting that at fundamental levels, the universe operates in ways that defy straightforward explanation. In light of superposition and uncertainty, our classical view of the universe as a well-ordered system with certain outcomes needs revising. Quantum physics introduces a level of fundamental randomness in the behavior of particles. This randomness is not due to incomplete knowledge or hidden variables, but is an inherent feature of the universe. Understanding and accepting these principles requires a significant shift in how we perceive the world, moving from a deterministic to a probabilistic view of nature. These quantum phenomena do not just alter our theoretical understanding, they also have practical implications. For instance, the principle of superposition is the basis for quantum computing, where qubits can perform multiple calculations at once, vastly increasing computational power over classical computers. Thus, exploring these concepts is not only about understanding the universe's fabric, but also about harnessing these properties for technological advancements. Quantum entanglement is perhaps one of the most fascinating aspects of quantum mechanics. This phenomenon occurs when pairs or groups of particles interact in ways such that the quantum state of each particle cannot be described independently of the state of the others, regardless of the distance between them. This interconnection means that the state of one particle instantly influences the state of another, a situation that Einstein famously derided as spooky action at a distance. The implications of entanglement stretch beyond mere theoretical interest. They challenge the very notions of locality and realism that are cornerstones of classical physics. Entanglement suggests that information can be transferred between particles faster than the speed of light, something that, according to relativity, should be impossible. This has led to numerous debates and experiments, most notably those by John Bell in the 1960s, which provided strong evidence that quantum mechanics predictions about entanglement are correct, even when they contradict classical intuitions. Moreover, entanglement has profound implications for the concept of information and how it can be manipulated and transmitted. In the realm of quantum computing, for example, entanglement is used to link qubits in a superposition state, significantly enhancing the power of quantum computers over their classical counterparts. This has potential applications in cryptography, where quantum entanglement could be used to create unbreakable encryption methods, as any attempt to intercept the message would necessarily alter the state of the entangled particles, thus alerting the sender and receiver to the breach. Entanglement also raises fundamental questions about the nature of reality. If particles can be so deeply connected that they instantaneously influence one another across vast distances, what does this say about the separateness of objects? This question touches on the philosophical as much as the physical, pushing us to reconsider how we define objects and their interactions in the universe. Understanding entanglement not only deepens our understanding of quantum mechanics, but also opens up new pathways for technology and philosophy. It exemplifies the strange, interconnected, and dynamic nature of the universe at the quantum level, a level that we are just beginning to exploit technologically and still striving to understand conceptually. The principles of quantum physics are not just esoteric ideas confined to theoretical physics. They have real-world applications that are transforming technology and our understanding of the universe. One of the most groundbreaking applications is in the field of quantum computing. Quantum computers use the principles of superposition and entanglement to perform multiple calculations simultaneously, offering the potential to solve problems that are currently beyond the reach of classical computers. Quantum mechanics also plays a crucial role in the development of new materials and technologies. For example, scientists are using quantum principles to develop superconductors that can conduct electricity without resistance at relatively high temperatures. These materials could revolutionize energy transmission and storage, leading to more efficient power grids and cleaner energy solutions. Additionally, quantum physics is integral to the field of cryptography. Quantum cryptography uses the principles of quantum mechanics to secure data in a way that is fundamentally protected against hacking. For instance, quantum key distribution, QKD, uses the properties of quantum bits or qubits, which are inherently secure due to the laws of quantum physics. Any attempt to eavesdrop on the transmission changes these properties, alerting the sender and receiver to a security breach. The practical applications of quantum physics extend to everyday technologies as well, such as the development of lasers and MRI machines. These technologies rely on the principles of quantum mechanics to function and have become integral parts of modern life. From healthcare to communications, quantum physics is proving to be a powerful tool that not only challenges our fundamental understanding of the universe, but also drives innovation in multiple technology sectors. As we stand on the brink of the quantum age, the future possibilities of quantum physics are vast and exciting. The ongoing developments in quantum computing are poised to revolutionize industries by handling complex calculations related to artificial intelligence, drug discovery, and financial modeling more efficiently than ever before. This could lead to breakthroughs in medicine, where quantum computers could simulate molecular interactions at an unprecedented scale, potentially accelerating the development of new drugs. Furthermore, the principles of quantum entanglement are being explored for use in quantum networks, which could form the basis of a new, extremely secure internet. Quantum networks would use entanglement to transmit information in a way that is inherently protected from interception, creating a new standard for security in digital communications. The exploration of quantum physics is also leading to new insights in fundamental physics, potentially helping us to unify gravity with the other fundamental forces of nature in a theory of everything. This could eventually lead to technologies that we can scarcely imagine today, such as warp drives or quantum teleportation. Moreover, the ethical and philosophical implications of quantum technologies are profound. As these technologies become more pervasive, they will challenge our concepts of privacy, security, and fundamental science. The quantum future will require not only technological adaptation, but also a rethinking of the societal norms that govern our use of technology. In conclusion, the journey into quantum physics is not just about understanding the universe at its most fundamental level. It's also about harnessing that knowledge to push the boundaries of what is technologically and philosophically possible. As we continue to explore these strange and wonderful aspects of nature, we stand on the cusp of a new era where quantum physics shapes our technology, our society, and our understanding